The Btree index is the default index type in Oracle. This index type is known as Btree because the table row identifier, rowid, and associated column values are stored within index blocks in a balanced tree-like structure. Oracle Btree indexes are used for the following reasons: improving SQL statement performance. A Btree index creates a multi-level tree structure that breaks a database down into fixed-size blocks or pages. Each level of this tree can be used to link those pages via an address location. The Btree enables the database to find a leaf node quickly. The tree traversal is a very efficient operation. Because Btree indexes store the actual key values in the index structure, the index can grow large. Btree indexes also have limitations on the length of the key they can store. While using Btree, database can make use of binary search on the leaf nodes as the data is stored in the sorted order. The Btree index is a tree data structure with a root and nodes. The tree is balanced because the root node is the index value that splits the range of values found in the index column. A bitmap index is a special kind of database index that uses bitmaps. Bitmap indexes have traditionally been considered to work well for low-cardinality columns, which have a modest number of distinct values, either absolutely or relative to the number of records that contain the data. Bitmap indexes are widely used in data warehousing applications, which have large amounts of data and ad hoc queries but a low level of concurrent transactions. Bitmap indexing provides reduced response time for large classes of ad hoc queries, reduced storage requirements compared to other indexing techniques, dramatic performance gains even on hardware with a relatively small number of CPUs or a small amount of memory, efficient maintenance during parallel DML and loads. Fully indexing a large table with a traditional Btree index can be prohibitively expensive in terms of space because the indexes can be several times larger than the data in the table. Bitmap indexes are typically only a fraction of the size of the index data in the table. The advantages of using bitmap indexes are greatest for columns in which the ratio of the number of distinct values to the number of rows in the table is small. For example, on a table with 1 million rows, a column with 10,000 distinct values is a candidate for a bitmap index. A bitmap index on this column can outperform a Btree index, particularly when this column is often queried in conjunction with other indexed columns. And/or conditions in the where clause of a query can be resolved quickly by performing the corresponding Boolean operations directly on the bitmaps before converting the resulting bitmap to rowids. Local and global indexes are used for partition tables in Oracle databases. Each index created on a partition table can be specified as either local or global. When you create an index on the whole partition table rather than for each partition, then it is called a global index. The main difference between these is that global index is created on the whole table but local index is created per partition. Local partitioned index maintains a one-to-one relationship between the index partitions and the table partitions. The second method is called global and allows the index to have any number of partitions. Indexes can be unique or non-unique. Unique indexes guarantee that no two rows of a table have duplicate values in the key column or columns. Non-unique indexes do not impose this restriction on the column values. Oracle Database enforces a unique key or primary key integrity constraint on a table by creating a unique index on the unique key or primary key. Function-based indexes facilitate queries that qualify a value returned by a function or expression. The value of the function or expression is pre-computed and stored in the index. To eliminate or reduce fragmentation, you can rebuild or coalesce the index. Rebuilding index creates new tree, shrinks height if applicable, quickly moves index to another table space. Higher costs, requires more disk space, enables you to quickly change storage and table space parameters without having to drop the original index. Coalesce index, cannot move index to another table space, lower costs, does not require more disk space. Coalesces leaf blocks within same branch of tree, quickly frees up index leaf blocks for use. When creating an extremely large index, consider allocating a larger temporary table space for the index creation. You can create and rebuild indexes online. Therefore, you can update base tables at the same time you are building or rebuilding indexes on that table. You can perform DML operations while the index build is taking place, but DDL operations are not allowed. Parallel DML is not supported when creating or rebuilding an index online. As your database grows in size, consider using index compression to save disk space. Creating an index using prefix compression, also known as key compression, eliminates repeated occurrences of key column prefix values. Prefix compression is most useful for non-unique indexes with a large number of duplicates on the leading columns. With the alter index statement, you can rebuild or coalesce an existing index, deallocate unused space or allocate a new extent, specify parallel execution or not, and alter the degree of parallelism, alter storage parameters or physical attributes, specify logging or no logging, enable or disable prefix compression, mark the index unusable, make the index invisible, rename the index, start or stop the monitoring of index usage. Oracle Database provides a means of monitoring indexes to determine whether they are being used. To start monitoring the usage of an index, issue this statement: alter index monitoring usage. Later, issue the following statement to stop the monitoring: alter index no monitoring usage. The view user_object_ usage can be queried for the index being monitored to see if the index has been used. The view contains a used column whose value is yes or no. Monitor index efficiency of space usage at regular intervals by first analyzing the index structure, using the analyze index, validate structure statement, and then querying the index_stats view. Consider dropping an index if it does not speed up queries. The table could be very small, or there could be many rows in the table but very few index entries. The queries in your applications do not use the index. The index must be dropped before being rebuilt. Oracle has chosen the database block size to match the index node, such that an index in a 2K block size will hold less key information than a 32K block size. As an Oracle table receives new rows from SQL inserts, the index blocks become full and the index node splits into two nodes. There are two types of changes to an Oracle index tree. 1. Index splitting. This is the most common change. When an index node is filled with keys and a new index node is created at the same level as the full node. Splitting widens the Btree horizontally. That is, index grows horizontally where multiple new level of index are created as data is inserted into table. When an index leaf block is full and a new row has to be inserted in the block, Oracle will usually allocate a new leaf block, split the contents of the full block fairly evenly between two leaf blocks, then update various pointers to bring the index structure up to date. At various moments in this process, the branch block above the leaf block and the leaf blocks either side of the splitting block have to be pinned. The number of times this happens is reported under the statistic leaf node splits. 2. Index spawning. This is when an index creates a new level. Index spawning is the process where the index grows vertically, index height increases. There are two types of index splitting, a 50-50 split and a 90-10 split. We have a 50-50 block split, where a new block is created and half the entries are contained in each of the blocks after the split. In a 90-10 index block split, we usually see that the data is being loaded in the same order as the index key. Index leaf node contention happens when rows are inserted based on a user-generated key, i.e. a sequence, and because the sequence key is always the high-order key, each insert of a low-level index tree node must propagate upwards to the high key indicators in the Btree index. The following is true about index splitting events. Small block size indexes will split more often than large block size indexes. This is because Oracle has made the index node the same as the block size. A 32K index node will hold more entries than a 2K index. Oracle data loading affects the types of splitting. Well-ordered data will have a 90-10 index split, while unordered data loads may result in a 50-50 index split. Index splits are permanent. At delete time, Oracle will not coalesce index nodes. Instead, Oracle will mark the empty data block as a deleted leaf node. The only way to remove imply index splits is to rebuild or coalesce the index. Index splitting can cause contention. If another session is doing DML data while another task is attempting an index access, the the task must wait on that index block split until it is finished. This is called an index block split wait event. After the index block split finishes, the first task will retry the index lookup. PCTFRE affects index splitting. The PCTFRE specifies the amount of space to reserve for later updates, and a large amount OS reserved space results in less room for index entries, causing more index splitting. Reverse key indexes literally reverse the bytes of the key value in the index to reduce block contention on sequence-generated primary keys. It simply stores the values for the index in reverse order. A value such as 789 would be stored as 987 in a reverse index. Oracle shifts the order of the value transparently, so that a user in the previous example would input the value 789 and have the same value returned in a query to reduce contention and hotspots in indexes. A reverse key index is created by including the reverse keyword in the index creation. Create index T1_ID_IDX on T1, ID, reverse.